Okay, so I'm gonna start with the introductions. Thank you everybody for being here in the SNAPP seminar. Today, it's our pleasure to have David Goldberg giving a talk here in the seminar. David is an associate professor at Cornell Ori Department. Previously, he was the A. Russell Chandler III Associate Professor at Georgia Tech. He received his PhD in operations research at MIT in 2011 and his bachelor's in computer science from Columbia University in 2006. Dave's research is in applied probability on topics including optimal stopping control and options pricing, inventory and queuing model, asymptotic analysis, and large deviations, combinatorial optimization, and robust optimization. He's also the recipient of an NSF Career Award, the 2019 Infimum Applied Probability Society Best Publication Award, and several, I'm not going to go into, student competition Infimum awards. He's also an associate editor for the journals of Operations Research and Stochastic Models, and the vice chair of the Infimum Applied Probability Society. So with that introduction, David, go ahead, please.
Great. So, hi, everyone. I know many of you, and for those who I don't know yet, hi, my name's Dave, and let me talk about just quickly two really important bits in that bio, one of which wasn't mentioned. So, really important bit one is that I am a co-organizer of the upcoming Stochastic Networks Conference, which is going to be held this summer at Cornell University in Ithaca. And let me just make a pitch that I think, those who attend the SNAPP seminar are exactly the kind of people, both, more senior people, but also students for whom that conference could just be a tremendous opportunity and a great experience. The Stochastic Networks Conference has a rich tradition spanning many decades with, luminaries of research in the applied probability community and beyond. I know the pandemics, made everything a bit complicated, but this summer we're fully in person in Ithaca. We're very excited. It's going to be a great conference, and we really hope you can join us there. If you have any questions about that, feel free to email me. That's point one. And bit two, just to kind of emphasize one other point. So as Mariana said, I am the vice chair and soon to be the chair of the Informs Applied Probability Society. And let me take a moment to express my profound gratitude to the organizers of the SNAPP seminar, not just for inviting me to give a talk, which is a privilege, but much more importantly, for providing this outstanding mechanism to kind of create this sense of community during the pandemic, which I think is, something that's extremely valuable. And I think going forward, we were actually just talking before the start of the talk, really brainstorming on ways to make sure that as we come out of the pandemic, that sense of community, of academic community, of kind of scholars coming together to interact and study these important topics that we work on, just how important that is. So thank you very much to the organizers of the SNAPP seminar. Okay, so with that, let me dig in. So today I'm going to be talking about a topic that I'm very excited about. Some of the results are kind of completed work, and some of them are ongoing. And today's talk is called A New Approach to High-Dimensional Optimal Stopping and Control. And it is kind of a significant departure from past approaches to these kinds of questions. And this is joint work with one of my recent graduated students, Yilun Chen. And okay, let me take it away then. So let me start with the punchline. So optimal stopping, which I'll refer to as OS, has kind of been a core kind of workhorse kind of problem in financial mathematics, operations research, stochastic control, economics, computer science for many years now. And the problem especially became kind of extremely well studied in the early 90s when it was realized that this problem in mathematical finance called options pricing could essentially be formulated this way. So, and let me also point out that optimal stopping, and I'll talk about formally what is optimal stopping here, has been really at the core of the study of approximate dynamic programming going back decades now. And because, as we'll see, it's kind of one of the simplest, yet kind of generally believed to be intractable high-dimensional stochastic dynamic programs. Okay, now there's already been several outstanding talks in the SNAPP seminar series, some of which you have seen related to optimal stopping. But let me point out a key distinction here. So I think a lot of those talks talking about variants of the secretary problem and certain kinds of online generalizations of that have typically been in a setting where things are either independent over time or kind of concentrate strongly over time. And that's, a lot of times when people see these secretary problems, you see IID things or independent things and stuff like that. So the whole point of today's talk and the problem we're going to talk about today is that it is on the complete other end of the spectrum of optimal stopping. In particular, we're going to be looking at problems that have a very non-trivial path dependence. So for example, it's going to be the complete opposite of IID. It's going to be that the values can have like long-range dependencies in some extremely complicated way. Furthermore, again, to just kind of on the opposite end of the spectrum of independent, the general setup is going to be that there's actually kind of a high-dimensional process which is being observed over time, such that the value you get when you stop is a function of that high-dimensional process. So again, just kind of as much complexity as you can put into this problem. And again, this has been kind of the version of it that was really at the heart of much of the original work on approximate dynamic programming, and then what later became kind of reinforcement learning and et cetera. We're also going to be looking at cases, we're not going to have any kind of assumptions about continuity or that things have niceness of that nature. It's just going to be the kind of nastiest, kind of variant of this without those kinds of continuity assumptions. And we're going to be especially interested in cases that have kind of a moderate to long time horizon. So, again, this was kind of at the heart of some of the early work on approximate dynamic programming, going back to the work of like Longstaff and Schwartz or, Ben Van Rooy and others. And the whole point is that when you have a high dimensional driving process like this, you have this so-called cursive dimensionality, which everyone is no doubt aware of. So you can't just solve the dynamic program because there are too many states. And again, one thing that's going to come up is kind of a repeating point in this talk is we need to separate out, there's the value you get when you stop, but that is a function of this kind of complex high dimensional thing, which indicates how it's evolving in the future. And so to solve the problem, you would actually need to keep track of all the possible settings of this high dimensional thing, which you can't do. So can't just solve the DP. So there's actually a vast literature on all kinds of approximate heuristic methods for this. Again, many of the early papers on approximate dynamic programming were very much on this theme. There arose, optimal stopping has been at the heart of the evolution of a lot of simulation-based methods for solving high-dimensional dynamic programs, which is really kind of using a dual approach. There's also been a tremendous amount of work about these kinds of optimal stopping problems using kind of PDE techniques and when you have kind of high-dimensional diffusions and all that kind of stuff. I'm not going to go into the details there, but again, there's kind of a truly vast literature across multiple communities. Even more recently, there's actually a line of work using deep learning for these problems. However, even if you take a look at kind of all these bodies of work that have focused on this problem, pretty much if you're looking for computational tractability plus kind of guaranteed error bounds, it's very limited. And effectively, in spite of this kind of vast amount of work, there's a lot of heuristic approaches that have demonstrated a strong numerical performance. There are some kind of methods that have guaranteed error bounds, but essentially the general wisdom was that you can't have both these things because it's a truly hard problem. And that's especially true when you have both high dimensionality and full path dependence. So it doesn't even have in an obvious way kind of even a high dimensional Markovian structure because it can have a full path dependence. So this is nasty stuff. And again, the common wisdom was just that, this is truly hard. And you know, one thing, we'll actually see several analogies at the end of the talk. I'm going to kind of talk about some additional high-level connections to reinforcement learning. But the general wisdom, which again goes back to early work in approximate dynamic programming, but also has been a theme in kind of, you know, some of the foundational works in modern reinforcement learning, is that for this kind of problem, you're either exponential in the dimension or you're exponential in the horizon, and that's it. You know, pick your poison, but there's no escaping this, and that was the, you know, the kind of common belief here. So what's the punchline of our work? So the punchline of our work is pretty much that that common wisdom was incorrect. And somewhat surprisingly, high dimensional optimal stopping actually, in a sense that we'll make precise, falls on the easy side of the line, which is kind of the opposite of what people believed across all these literatures for quite a long time. And, you know, then we'll have many questions throughout the talk about what else might be on the easy side of the line that we've been missing here in high dimensional control. So what do we prove? We prove that somewhat remarkably, there's what I'm going to go ahead and call a simple and elegant formula for optimal stopping as an infinite sum, which is quite surprising given that it's kind of this, you know, seemingly intractable high dimensional control problem. It's somewhat remarkable that, and I'll show you the formula, that what the first few terms look like. So, you know, it is kind of simple enough. It's kind of odd. But okay, even better, what I'm going to show you, and another kind of cool thing here is all the proofs are actually pretty simple. So I'll walk through much of the kind of logic of most of the proofs. Somewhat remarkably, if you truncate this sum after k terms, you actually can control the error, and it decays as 1 over k. And furthermore, as long as you don't go too far out in this series, the terms are actually not that hard to simulate, because the kth term only has a depth k nested conditional expectation. We'll talk about that more when we get to it. And so the bottom line is you don't have to go out too far in this series, and thus you never have to get to the terms that are actually hard to simulate. And so this actually yields efficient algorithms. Another way to think about this in the context of approximate dynamic programming or reinforcement learning is we develop kind of a totally automated, efficient, provably good basis function, essentially, that kind of tells you what to do as a function of this very complex high dimensional state. And what does that yield for us? That's going to yield efficient randomized approximation algorithms. And in particular, if you're willing to have epsilon error in your you know, what it outputs, it's going to have a runtime of like t to the poly 1 over epsilon. It really just like t to the 1 over epsilon. You know, we don't kind of optimize constants or anything in the current manuscript. Furthermore, and even nicer, and this is again part of why it's going to connect fundamentally to reinforcement learning and things of this nature, is it's totally data driven. So you don't need to have some weird density function or anything like that. It is purely sample driven. And the number of samples it needs is, of course, again, kind of for any fixed epsilon, just going to be a polynomial in the horizon. And let me point out also that it's effectively independent of the dimension, or kind of perhaps, depending on exactly how you want to do your accounting, you know, kind of linear in the dimension or something, but there's no kind of hidden scaling here with the dimension or anything like that. And kind of the takeaway here is, if for high dimensional optimal stopping, if you give me an efficient simulator, where efficient simulator just means that you can simulate this high dimensional process, you give me the simulator, I give you the algorithm. And that is kind of, again, the framework of this kind of generative reinforcement learning, where you can kind of input a state and get a trajectory. And again, the kind of mindset we have here, which to our knowledge for problems like high dimensional optimal stopping hadn't really been considered in this way before, is the flavor of our results is very much analogous to the concept of a PTAS, a polynomial time approximation scheme in computer science. Namely, the regime that's going to be of interest to us is fixed epsilon. And then you could think about like the dimension and the horizon and the dynamics all being quite nasty. But that epsilon of kind of the error you're willing to tolerate in your approximation is fixed. And again, a key point here is there's no hidden assumptions about like, oh, maybe I'm assuming that the dynamics are continuous, or maybe I'm assuming this or that, or embeddability or some low rank or something like that. Not at all. The only thing we'll assume is that the actual magnitude of the rewards are bounded. But even that isn't really essential. The general methodology can be massaged to get results under are different kinds of assumptions. But the point is here, there is no hidden assumptions about continuity or kind of nice densities or anything like that. And again, one thing I'm going to talk about in the second part of this talk is that this really is a potential hammer that might have significant implications for other high-dimensional control problems. I'll give one or two examples of that in the talk, but perhaps more importantly, I'm going to talk about a way to think about other high-dimensional control problems which suggests certain kind of links and analogies, which there's a lot of interesting open questions around. I'm also going to point people to some older literature which could be quite valuable, maybe for things you yourself are working on. Another interesting thing that's, again, it's a bit different from past works in this space is one thing we're going to keep coming back to is what I'll call the power of bounded nested computation. Because again, and we'll come back to this, right? It's kind of generally well known that if you have a T period control problem, irregardless of the dimension or the state space, if you're willing to do kind of a depth T nested conditional expectation, you can of course express it this way and simulate it. It's just kind of like a totally on the fly way to express the solution. And that typically in reinforcement learning and approximate dynamic programming is called the sparse sampling methodology, but this appears implicitly in many works over the years. But the common wisdom, of course, had been for a depth T problem, you need for a length T problem, if you really want to solve it, you need a depth T nested conditional expectation. But of course, computing depth T nested conditional expectations is very nasty and scales exponentially in the time horizon generally. So the somewhat remarkable, one of the remarkable implications about our work is that, in fact, with just very shallow nesting, and it'll be clear what I mean by shallow nesting when I show you the first few terms of this expansion, you can actually get really close. And in fact, the levels of nesting you need to get within 10% is totally independent of the horizon or dimension or anything else. I'll circle back at the end of the talk to some really interesting questions about what's the meaning of that, what other problems might something like that be applying to, how does this relate to other notions of kind of parallelism or adaptivity appearing in other literatures, etc. Great. So let me, I guess, I'll click the chat. Nothing yet. Okay. So cool. So let me move on. So, okay, let me make the model totally precise. So we're going to be in a discrete time T period problem. Let me point out that a lot of the same logic would in principle apply to a continuous time problem. Then you have like other subtleties, especially if you don't want to assume any kind of continuity. So we're not going to talk about that. We'll just be in the zone of a discrete time problem. So T periods, capital T is the length of the horizon. Now, we're going to have a kind of an information process, aka a filtration script F. And you could, if you don't want to think about filtration, you could just think about this as there is this high dimensional vector process Y, Y1, Y2, Y3, Y4. Each of these is a capital D dimensional vector, and it's evolving in a possibly very complicated way. And the point is that the value you get for stopping at a given time is just an arbitrary function of, the high dimensional Y vector, really the whole trajectory of high dimensional Y vectors up to that time. And those things can be evolving in an arbitrarily complicated kind of general way. Formally, the filtration would be kind of the sigma field generated by that thing, but you don't need to worry about that. You just think capital Y, high dimensional process evolving over time, and the value you get for stopping at a given time is just a function of all those Y's so far. Okay. And again, this is kind of just the classical setup of, this kind of pure high dimensional optimal stopping. For reasons that'll become clear from our approach, it's actually most natural to explain in a minimization context, although through some simple transformations. It can be put in a maximization framework as well, but because it's a little more natural, I'll be explaining in a minimization context. So instead of kind of rewards, we're going to have costs. And in particular, if you stop at time little t, there's a cost function, little g sub t, which takes as input the whole trajectory of these high dimensional vectors up to time little t, and outputs the cost if you choose to stop there. Okay. And right, the way it works is at any given time, you observe this trajectory of high dimensional y's. You see, if I stop now, what's the cost I'm going to get? You make the decision. If you stop, it ends. If not, time goes on. And we're going to denote this cost you get if you stop at time t as a function of the whole trajectory of y so far. That's going to be, we're going to call that zt. And you could just think about this as like, you're seeing this sequence of random variables, z1, z2, z3, et cetera, which have a very complicated dependency structure dictated by this common high dimensional process, which they're functions of, but they're just variables on a common probability space. So if you don't want to worry about the y's or anything like that, you could just think for the moment about, you have this sequence of random variables, z1, z2, z3, et cetera, with a possibly very complicated dependency structure between them. And if you stop at time t, you get zt, and you're trying to minimize. Okay. Assume everything's non-negative and integrable, so nothing ultra pathological. Another very important concept for us, of course, will be the set of stopping times. So what does an f-adapted stopping time mean here? It means that you have to be stopping based on the high dimensional vectors you've seen so far. Okay, and that's again just the kind of traditional meaning of high dimensional optimal stopping. Okay. And I guess for those who have never seen a stopping time or anything like that, it just means literally in each period, you get to observe the high dimensional vectors that have happened so far. And then you need to make the decision as a function of those in or out. Okay. And so the problem of interest is to minimize over all such stopping times the expected cost you incur when you stop this Z process. Okay. Now, a key point here is we assume access to a simulator for which you can input any partial trajectory of the Y's, hit a button, and get a sample of kind of the Y process going forward conditioned on that particular partial trajectory. And that's really the only thing we need for our algorithms to work, beyond, I guess, like addition and things like this. Okay. I guess let me pause there. I'll pause a few times throughout the talk. Let me pause there for and just see if there's any questions just about the setup. I don't know if I can, let's see, can I see if people raise hands? If you have a question, you can just unmute and shout it out.
What kind of a process is Y?
So Y, it doesn't even have to be a D-dimensional process. That's just to kind of simplify it for purposes of exposition. You just think about it like it's an RD vector valued process that the vector you go to the next period, the conditional distribution there can be an arbitrary function of the vectors so far. So it's just an arbitrary path dependent D-dimensional process.
All right. Okay.
No
So
assumptions are needed on that. Yeah.
Okay. Thank you.
Great. Other questions?
Yeah, so does the dimension D show up anywhere in your
No, this is just
Okay.
to make it concrete in people's minds. Otherwise, I don't want to throw around Hilbert or Banach or anything like that.
Yeah. Gotcha.
RD, but that's not essential. Yeah. Great. Thank you. Cool. Okay, so let me talk about the intuition and main results. So pretty much I'm going to walk you through the main proof now. And the proof kind of gives the algorithm and the answer in some sense. And so, and it also has some nice intuitions, which we'll later see connect to some of these possible generalizations to other control problems. So let's start with just a simple definition. I already told you opt is the optimal stopping value. Fair enough. Now, I'm going to define the random variable, which is the min of your z's. Okay, there's nothing hidden up my sleeve here. There's just a trivial definition of like, you know, if in hindsight you look back at all the values you'd seen, this would be that thing, the minimum. Easy. Clearly, you can't beat the expected value of the min. This is like the so-called profit inequality. If you got to look back at the end and select the smallest in a non-adapted way, that's how good you could do. Okay, so trivial, fair enough. Now, the whole secret, the different way we're going to look at it is I'm going to turn that inequality into an equality in a very special way. It's going to be, the math will be straightforward, but it'll have a magic to it. In particular, what I'm going to show you is that the actual optimal stopping value is E of min plus the optimal stopping value of a certain reduced problem. In which case, and that reduced problem is going to have a very simple, natural form to it. And then we're simply going to recurse and look at the expected value of the min of the reduced problem, and then the expected value of the min of the reduced problem, and etc. That will give us an expansion where each term has kind of a very nice interpretation. And we're truncating it will just give us something efficient. We can simulate it to get at the value, and that'll pretty much be how our methodologies work. I'll later show that this algorithm actually has an interpretation in terms of solving a max flow problem because of a certain kind of duality that actually connects to other control problems also. But okay, let me get to the nuts and bolts of this. So I said that opt is E of min plus a reduced problem. I claim that reduced problem is what I'm going to call a regret problem. Okay. So what I'm going to show you now is that the optimal value of the original problem is this simple profit thing, the expected value of the min, plus the value of a different optimal stopping problem, which I'm going to call the regret problem. Okay. So what's this regret problem? I'm going to define a notion of regret, which kind of coincides with the definition of regret many of you have probably seen in various kind of machine learning works, etc. But here we're going to define a regret process. So what is the regret process? The regret process says the following. It is the process defined as follows. At time t, the regret process is zt, the kind of actual, the tth variable in our actual process, minus my best guess of the all-time min of the z's at that time. So it is literally, in some sense, like if I haven't stopped yet and I were to stop now, regret sub t is conceptually just how bad am I doing relative to my best guess of this kind of profit all-time min at that time. And to put it, again, just totally formally, the regret process at time t is just my actual process at time t minus the conditional expectation of the all-time min, which is unachievable. So the conditional expectation of the like best in hindsight, given the information up to time t. Let me point out two things that'll come back later. Notice first that the regret process is non-negative. Why? Because z at a given time is certainly at least my best guess of the all-time min at that time, because the all-time min has baked into it the one I'm looking at now. Okay. Let me also point out that since the regret process is my original process minus some kind of best guess, it's going to be lower. So this process is lower than my original process pathwise. Okay, it's like it's reduced in the literal sense of the values are lower. Okay. In which case my regret problem is just going to be literally the optimal stopping problem of the regret process. So if I stop at a given time, I get z tau minus, if I stop at a stopping time tau, I get z tau minus this is the Doob martingale of the all-time min evaluated at tau. Okay. Let me pause there for 10 seconds and just see if there's any questions about that. Because if we get this slide, it's pretty much much of the conceptual underpinnings of the approach. Any questions about just what I've said so far?
Hi, can I ask a question? I'm not sure if it's too early to ask this.
Please.
Dave, I'm not sure if it's going to talk about the relationship between information relaxation of Brown's paper.
I will come back to that. Yes, that's explicitly in the talk. Yep.
Okay, thank you.
Yeah. Good.
Maybe a couple of notational questions, if that's okay.
Please.
Yeah. So min is the min over infinite time, or
Well,
is it up
it's
to
just
some
capital
time,
T. There's capital T period. So
okay, so that's
min
the
is
time
just
horizon.
literally, so we have this stochastic process of the z's.
Yeah.
Min is just literally the minimum of the z of all the z's.
Okay, so little t is less than capital T, and this
Yep.
is sort of the guess at the min
Yep.
overall time, given
Exactly.
what's happened so
Yes.
far. Okay, and the regret, usually when they define a regret, it's sort of a sum, like a cumulative thing, whereas you
Yeah, no, this is not literally the regret notion.
Yeah,
we
yeah,
used to.
okay.
It's just
That's
kind of analogous, similar concept that comes up here in a nice way.
Fine, okay. That's
But it's
okay.
not
Okay,
literally
yeah.
the notion of regret from, paper X or something like that.
Yeah, that's fine. That's okay. Okay, good. Great. Thanks.
Make sense?
Yeah, yeah.
Thank you. Other questions? Good questions. Okay. So observation 1, and that is actually a picture I Googled of Doob. So just by Doob's optional stopping theorem, for any given stopping time, the expected value of the regret process evaluated at that stopping time is going to be the expected value of the Z process at that stopping time minus something that has nothing to do with the stopping time, because by optional stopping, since the regret process is ZT minus a martingale, because it's like the Doob martingale of the all-time min. If I take the expected value of that Doob martingale at a stopping time, I just get E of min. The stopping time goes away, and that's this classical optional stopping theorem, which I'm sure most people know. If you're a starting PhD student, you may see this in one of your early classes, but it's a nice property of martingales that if you take the expected value of a martingale at a stopping time, you just get the expected value of the martingale at a regular time, which is just going to be just the expected value of the thing on the inside or the expected value of the min. Okay. But now if we just take that literally and consider our regret problem, we find just since, for every tau, you can replace the expected value of regret tau by E of Z tau minus a constant, then of course, minimizing over tau for the regret process is the same as minimizing over tau for just the Z process, because it's just shifted by a constant. So it doesn't affect the optimization problem. Okay. But if we just rearrange that, we realize here we have the regret value is the optimal value minus E of min. If we just move E of min to the other side, we get the optimal value is E of min plus the best we can do on the regret process. Okay. And that is what we're going to need to kind of kickstart a recursion, which is at the heart of our whole approach. So we've already done 80% of the work. And let me point out, as was alluded to with the question about information relaxation, there are many, many kind of dualities out there. And in fact, although I don't know if I'll get to it, but in the Q&A, I'm happy to go to it. It's in the slides. There are many duals out there, and it's well known that martingales interact with optimal stopping in this nice way. And there's a whole duality theory of optimal stopping involving martingales. However, the fact that using E of min given FT in this way and recursing it creates this kind of magical chain reaction, which none of these other kind of approaches had gotten at before. Even though they had kind of vaguely general related ideas were there, doing it this way in this way and recursing it yielded this kind of somewhat surprising kind of insights. Okay, since this is kind of like the crux of the argument, we're just going to recurse now. Let me pause for a moment and again, just give 5 more seconds if there's any question just about the basic math on this slide. Okay. So all we're going to do now is recurse and expand by taking literally the regret optimal stopping problem. So we just established that the optimal value of our original problem is this kind of trivial expected value of the min, which is this kind of, just this profit term, plus the best we can do on the regret problem. All I'm going to do now is define the regret problem of the regret problem. In particular, I'm going to define a regret 2 process, where the regret 2 process at time t is my regret process at time t minus the conditional expectation of the minimum of my regret process, given the information up to time t. In which case, just doing literally the same exact logic before, but pulling out E of min of the regret process, I get that my original optimal stopping problem value is the kind of expected value of the min, the typical profit thing, plus the expected value of the min of the regret process, plus the best I can do on a new reduced problem. And of course, then I'm just going to define the regret 3 process to be the regret process of the regret 2 process, et cetera, et cetera. And we can just kind of continue in this way. And we get, for any k, opt is going to equal E of min plus E of the min of the regret 1 process plus E of the min of the regret process, et cetera, plus a kind of remainder term, which is always going to be the best I can do on the k plus first regret process. And let me also point out, so a few kind of base order sanity check questions people might have. So point 1, the regret process is not degenerate. If it was degenerate, then either the math here would be wrong or something crazy would be happening. So no, the regret process is not degenerate. Reason being that until you're at the end, in general, the regret process might be kind of lower than where you're at, because it could be like, well, there's things you haven't seen yet. But once you're at the end, it's going to look like the last term minus the min of everything. And unless the minimum happens to occur in the last period, in which case something kind of special does happen, it won't be degenerate on either end, and it's just not degenerate in general. It's a meaningful process. So let me draw the first few terms of this expansion, just so you get a kind of a feel for it. So the first term is, again, this kind of classic profit term, E of min, nothing magical here. The second term is the expected value of the min of the regret process. So what is it's the minimum of what? It's the minimum of a bunch of terms where the ith term is original process at time I minus my best guess of the min of all the j's given the information up top. And the third term is going to be, I won't kind of go through it in gory detail, but again, it's just the previous thing kind of composed in that precise way by the operator, min of previous thing minus best guess of min of previous things up to time t. And it goes on and on and on. And you get this very structured, kind of a visually appealing kind of sum. And it turns out that under very general conditions, that error term goes to 0. And that if you do the sum out to infinity, it does give the actual optimal stopping value. Now, another key point is this, and this has to do with the nesting. Notice that the first term, E of min, of course, this can be computed efficiently by simulation, right? I just draw, I don't know, pick your favorite kind of concentration thing. I draw 1 over epsilon squared trajectories. Along each of them, I take the min, I average them. That gives me a good estimate for E of min, right? Again, assuming that the z's have at least reasonable moments or they're bounded or something like that. Okay, so clearly computing E of min by simulation is easy enough. What about the second term? Well, the second term is clearly more complicated, but how would I compute it? I would draw one trajectory. So I will repeat the following. Draw a trajectory. Now I go down through the trajectory, and at each time, I need to compute one extra conditional expectation by drawing a bunch of trajectories. So I have this one trajectory with a bunch of, for each time there, trajectories hanging off of it. And I'm going to repeat that thing 1 over epsilon squared times. Because for each one outer trajectory, I need to estimate a bunch of conditional expectations inside of it. But okay, that's going to have complexity roughly t squared over epsilon squared or something like that. Really, if you want to be precise, it's going to have a worse scaling in epsilon. I won't talk about the particular way epsilons propagate through nesting, but up to kind of, for any fixed epsilon, it's going to be roughly like t squared. Okay, because again, for each one trajectory, you're going to have all these trajectories hanging off of it. But nonetheless, it's just a depth 2 nested conditional expectation t squared. The next thing is going to be a depth 3 nested conditional expectation t cubed, and et cetera, et cetera, et cetera. Because for the third term, you're going to draw a trajectory. Now, for each of the t's, you're going to have to do what looked like the second term, which is going to be kind of a t squared thing. So you're going to have t cubed. But the bottom line is kind of to go out to k terms, you're never getting to a recursive depth beyond k. And again, to be clear, now it is true that at each of those kind of recursive depths, you're doing something of depth t. But nonetheless, that means it's only scaling kind of computationally like t to the k. Now, let me contrast that for a moment with the kind of traditional way that in control people think about nesting, which would be, okay, you use backwards induction, you get, you know, E of min of Z1 and a conditional expectation of this and that and that and that and that. That's a completely nested thing with a depth of recursion of t, which is going to have a complexity scaling exponentially t. So it's just really a very different type of recursive thinking. And again, the key point is that it is of shallow depth. Now, here's an example of a kind of theorem that we get. So a kind of theorem we get is that, for example, if your z's are bounded between 0 and 1, again, this is nothing about the dynamics or anything, just if the values of the z's are bounded between 0 and 1, then if you truncate that series at k, you get an error of like 1 over k, 1 over k plus 2, but it doesn't matter. And essentially, the rate of convergence, the number of terms you need in that series is independent of t, the dimension, the dynamics, anything. Now, depending on the assumptions you want to make, so if you assume it's bounded in 0, 1, that's like the cleanest thing. If you want to make different assumptions, you often can show kind of a different rate using kind of related arguments. For this talk, I'm going to focus on the case where the values are just bounded between 0 and 1. But again, let me stress, in contrast to kind of essentially all past approaches, there's nothing assumed here about any dynamics being continuous, nothing, nothing at all like that. Just that the rewards are kind of bounded, at least for these specific results here. Okay. So I'm just going to sketch the convergence proof. I won't go into the details. And actually, the proof in the paper, to get the 1 over k, you need a slightly more sophisticated argument, which I'm not going to go into here. It's still pretty easy. Here, let me sketch the intuition, which would give kind of a slightly weaker bound, but we do use it for some other results in the paper, and it's very simple. So, right, like I said, opt equals E of min plus E of the min of the regret 1 process plus E of the min of the regret 2 process up to k plus this remainder term. So we already claimed that the regret processes are decreasing, right? We're constructing on one probability space, regret 1, regret 2, regret 3, regret 4, etc. So they are literally, regret 2 is on a given sample path below regret 1, because regret 2 comes from regret 1 minus kind of a min of the regret 1. So these processes are decreasing. So of course, the expected value of their minima are decreasing. So in other words, the expected value of the min of regret 1 is bigger than the expected value min of regret 2, bigger than the expected value min of regret 3, etc. Just because literally we've constructed these processes so they are sample path-wise on the same probability space decreasing. Not decreasing in time, but decreasing as you go from regret 1 to regret 2 to regret 3. Which means that we have an expansion for opt that's like of the form, we're adding up, I'll let AI be this E of min of regret I. Then our expansion, ignoring the E of min term just for a moment, our expansion is like, we could call that like regret 0, but it doesn't matter. Our expansion is like A1 plus A2 up to AK, but where these AIs are decreasing, because we already said the expected value of the min of regret 2 is less than the expected value of min of regret 1, regret 3 less than 2, etc. So our solution is like adding up a bunch of things that are decreasing. Now, of course, they can't add up to more than opt, because opt is equal to them plus a non-negative remainder. But of course, if A1 plus A2, etc., can't be more than opt, and the A's are decreasing, it has to be that AK plus AK plus AK plus AK can't be more than opt, because A1 plus A2 up to AK is bigger than AK plus AK plus AK plus AK. Okay, but that means K times AK is at most opt, and since the problem's bounded, that's at most 1, which means AK is at most 1 over K. Okay, and again, all that we were using here is we have an expansion, which is non-negative, and for which the terms are increasing. And our assumptions imply that the actual value being approached is bounded. Now, our error term there is not E of min, right? Our error term is an optimal stopping problem on regret K plus 1. If our optimal stopping was E of min of regret K plus 1, we'd be totally done. However, it's kind of classically Ted Hill, who's worked on many things in this space, had already shown it, but you can also show from first principles that if the expected value of the min is small and the problem is bounded, then the optimal stopping value also has to be small. It's something like epsilon goes to root epsilon or something like that. And if you just want a naive version of this, you could just use Markov's inequality and say, oh, consider the following, if I know E of min is small, here's a stopping strategy. Stop as soon as you get to some multiplier of that small E of min value. If that ever happens, you're still stopping at a small value. If it doesn't happen, just stop at the end, which is at most 1. But it really should happen because E of min is small, and you could just use Markov's inequality. But again, this was already understood. Our proof in the paper doesn't quite go this way. But again, it's quite intuitive that if E of min is small, then it should be that the corresponding stopping value is also small. Again, our real proof actually uses a sample path argument. It's not like that hard. It's just a little less intuitive. So I'm not going to explain it here, but I'm happy to talk in the Q&A about it. But really, this is the core logic of why you get a 1 over K kind of convergence, is that you have these terms that are decreasing. That's it. So let me pause. Is any questions?
I have a question.
Please.
So your algorithm seem to provide a way to calculate opt, but do you actually find the policy?
Yeah, good. So yes, yep. I'm going to talk about that in a moment. Yes. So we get both these things. There's many ways to do that conversion. It turns out, in fact, that it takes a few manipulations. You can actually just stop. The higher level regret process actually tells you when to stop. That's not obvious. You can also just do it to go. You can do a resolve, which also works. So it's either way is fine. I won't go into all those details, but I will on this very slide talk about that. So what are some algorithmic implications here? So as we said, the terms of this expansion can be computed by simulation, where as long as you don't go out too far, you're getting a complexity like t to the whatever term you're at. But since you only need a few terms, you end up with no poison from the dimension and no poison from the horizon beyond a polynomial poison. So kind of past approaches, we're thinking you're either expo in the dimension or expo in the horizon. Here, if you're willing to accept epsilon error, you're fine in the dimension and you're poly in the horizon, which is a very mild poison, or in traditional complexity sense, no poison at all. It's completely data-driven because all you're doing is simulating these kind of terms. And again, to go to the actual stopping strategy, there's a few ways to do it. You can either at each time kind of estimate the to-go value, or you can actually use this kind of essentially a regret 1 over epsilon process to decide when to stop. I won't go into those details. So as I said, it is true that as you go to more and more terms, it's becoming more complex, but provably you only need a few terms. The exact runtime will depend on the specific assumptions and exactly what notion of approximation you want, like whether you want additive approximation, epsilon approximation, whether you want to assume the reward process is bounded, or just that it has some kind of controllable moments or something. That'll get you the exact nature of kind of the trade-off. But the general point is going to be epsilon approximation in time t to the 1 over epsilon, essentially. Now, there will be some kind of epsilon prefactors that are a little nasty, and I'm happy to talk about that in the Q&A. And you indeed also get efficient stopping strategies. For example, it turns out you can use the high order regret process to decide when to stop. You can also do kind of a to-go resolve if you so incline. A key question is, okay, it's still true that if the horizon is long, this is the kind of classic kind of PTAS issue. Although, yes, this is the first method that's not kind of exponential in the horizon without suffering from other kind of poisons. It's still true that going out beyond depth 3 or 4, at least as far as I understand it, is pretty challenging. And so a key question is, and we have some ideas here, but is some kind of, this opens the door that maybe there are expansions that look very, very different from the kinds of expansions that people have done before. And you can think about everything like an expansion. You think of policy iteration like an expansion, everything's like an expansion. And so the question becomes, for this problem, but really for other problems also, when can there be kind of an expansion for which a constant number of rounds suffices and kind of what gets you there the fastest? Or furthermore, what structure can you impose so that some of these expansions might go faster? So, okay. So now, let me, in the last few minutes, let me just kind of, and then in the Q&A, I can go into a lot more high-level thinking and questions. Let me comment a little on whether this goes beyond optimal stopping. So the preliminary answer is yes, but at this point, we have many more interesting questions than answers. So let me first point out a very natural generalization, but which does actually capture a broad range of problems in also operations management. And that's multiple stopping with a bounded number of stops. And so pretty much you can kind of plug this recursion into a meta recursion related to how many stops you have left. And you get a runtime that's like, instead of t to the 1 over epsilon, something like t to the maybe L squared over epsilon or something like that. And this can actually handle very general types of control problems where you can only change action a bounded number of times. It can depend on the history of your own actions in a very complicated way and all this stuff. So that's point 1. But let me talk about, for a moment, a much more general connection. And then I know we're going to run out of time. So I'll talk about this for a moment and then end on a slide with a bunch of questions. And then in the Q&A, I'm happy to talk about those things. So let me take a detour to what I call high-dimensional control as a problem on a big tree, which certainly relates to information relaxation, but even more importantly, relates to a precursor of information relaxation by Rockefeller and Wetz, and work in the stochastic optimization community on so-called scenario tree ways to think about stochastic optimization. So let's suppose, let me explain what I'm trying to get at here in the context of optimal stopping. Simple 3-horizon problem. And suppose this complicated generating process Y is just one-dimensional and binary. This is just to illustrate a point. You don't need this for this kind of analogy I'm going to present to be true. It just makes it visually simple. Okay. So what do I have here? I have a depth 3 tree that's kind of just a binary tree. And I've labeled the edges based on kind of how you've branched. Notice that for each possible trajectory of this kind of driving process, we have a path from root to a leaf. And right, we have a label for every kind of intermediate step on any of the paths. Okay. And I claim at the highest level, stochastic control, just broadly, is assigning an action to each edge for any kind of control problem, or for any kind of control problem. You can just write out a tree, which is like, how has the system evolved up till now? And then you need to decide for every possible now what you want to do. Okay, that's just very high level. So what does this mean for optimal stopping? I know this, we're going to make it a little concrete now. So, right, so here's a stopping time. Let's stop if y1 is 0, or the y process up to time 2 is 1, 0, or the y process up to time 3 is either 1, 1, 0 or 1, 1, 1. Right, in tree world, this is just slicing certain edges of my tree in such a way that, and you'll notice this does coincide to a stopping policy because it has that kind of, no path has kind of 2 stops, right? Every path has 1 stop, so this is a stopping time. but it just coincides to like, I'm going to slice certain edges of this big tree. Okay, now I'm going to take this analogy even further. And to do that, let me for the moment suppose that the y's are not just binary, but they're actually IID Bernoulli a half. So extremely simple case. What I'm going to do now is add another layer to this tree so that I can read off from the tree what the expected value of that stopping time is. I'm going to give the tree a very particular kind of extra layer. And in particular, I'm going to label each edge of the tree with essentially what's the probability that if I never stop, I would get to that edge of the tree times what is the value I get if I stop on that value. So in particular, to the first two edges of the tree, I get 1/2 times the value I get if I stop at 0. And on the other side, I get 1/2 times the value if I stop at 1. If I go down again, because they're IID Bernoulli, right? If I never stopped, what's the probability I would get to 0, 0? It would be 1/4. And what's the value I get if I stop at 0, 0? It's G of 0, 0. And I'm just going to decorate all the edges of the tree in this way. However, I claim now that the expected value of that stopping time is just the sum of the values on the edges I've cut. Right? Because it's just going to be, well, what if I get 0 right away, then I stop, I get G of 0. So that gives me a term to the expected performance of the stopping time of 1/2 G of 0. Alternatively, if instead of seeing 0, I saw 1 and then 0, which happens with probability of 1/4, I'm going to get what I would get if I stop at 1, 0, which is G of 1, 0, and I get those two terms with an 1/8 also. So, okay. Which shows that for this stopping time, I can actually express it as the value on a certain cut in this tree. And it turns out that, and it's again kind of intuitive, since stopping time is saying for each trajectory of my high dimensional information process, when should I stop? And right, the min cut problem in a graph is saying for every path from the root to the kind of leaves, where should I cut the graph? It turns out that optimal stopping is exactly solving min cut in a big tree like this, rigged in this way. For a general information process, instead of 1/2 and 1/4, etc., it would just be the general probability of me getting there times the cost of me stopping there, and there'd be way more than 2 branches. It's going to be this massive tree. But the point is, our algorithm can actually be interpreted as a randomized iterative method for solving this min cut problem as a max flow problem, where those kind of regret min things we have there can be interpreted as how much we push in different rounds of kind of a flow algorithm. So in particular, in the first round, if we wanted to interpret our algorithm in terms of solving flow on that network, what we would do is on each trajectory of this tree, I'm going to push. So on the trajectory, which is 0, 0, 0, which is just the leftmost trajectory, I'm going to push the minimum of all the values along that path, which is going to be the minimum of G of 0, G of 0, 0, G of 0, 0, 0, times an 1/8. And on every trajectory, I'm going to push the minimum of the values along that trajectory times the probability of that trajectory. And kind of the first round of our algorithm can be interpreted as pushing flow like that in a max flow problem on a tree like that, where again, since min cut and max flows are dual of each other, that's kind of the connection there. But let me point out that, right, if I had to literally track all the paths in this tree and kind of manually push the minimum along each of them, I couldn't do it because the tree is this coming from this high dimensional thing. There's way too many paths. I couldn't do it. And indeed, the paths will scale with the number of states in the dimension. However, in our method, we don't actually have to think about what goes on each individual path. Instead, we just compute E of min, which we can kind of sample by just randomly selecting a few trajectories and kind of seeing what it looks like there. And so in particular, our algorithm can be viewed as a certain implicit simulation-based way to iteratively solve max flow on that tree, where you never have to decide what you're going to do on every single path. You just do it all kind of implicitly by simulation. And again, let me point out that other methods considered in the literature, and I'll end after this slide and jump to the Q&A. Other methods considered in the literature have also done implicit things. And again, the classic example is kind of sparse sampling, where that's just this classic, you can always solve a length t control problem by a depth t nested conditional expectation. That would be equivalent to solving this big tree problem by kind of, you start at the leaves and you say, how much can I push 1 level up, 2 levels up, 3 levels up? And you do all those by kind of a deeply nested conditional expectation. But that's going to have a deep nesting. Our approach is doing this kind of implicit simulation thing with only a small level of nesting, which is different from kind of all the other ways that have been done before. And let me just say that, and now I'll just jump to the Q&A. Let me say that just to kind of get the Q&A rolling, there are all these dualities out there. The fact that there was this max flow min cut duality actually connects to some of those dualities. And one generalization that we have preliminary results for here is another interesting online problem that, if you look at it the right way, the dual problem becomes a max flow problem. And that's actually online bipartite max weight independent set, because there's some classical results in kind of combinatorics that bipartite max weight independent set can be solved as a flow problem. And again, to kickstart the Q&A, what I'll say is that there are several kind of duality theories out there that think about high dimensional control in terms of trees like this. And yes, information relaxation of Dave Brown and others can be viewed that way. However, let me say that one work that I think stochastic optimization as an academic community kind of knows very well and has continued to work on, but in control, it is the precursor of that work by Rockefeller and Wetz, which brings some additional insights into that, which are really useful in thinking about for which other kinds of big tree problems might the dual problem be solvable in a constant number of rounds. And I think there's actually, there may be some really interesting stuff there. And maybe I'll end the talk there and jump to the Q&A. There's a lot of stuff. Yeah, there's tons of interesting things this connects to, and I hope very much in the questions and answers we can get to it. And maybe I'll just very quickly, 2 big questions. Big question 1, when can we solve high dimensional control without the poison? Ideally with a bounded number of iterations of some kind of very smart iterative process, which is, just hasn't been looked at before. And 2, another thing that keeps coming up, and I know it's coming up in many kind of areas in kind of applied probability control OR now, is there's a deep philosophical question about what does it mean for a problem to say, you give me a simulator, which is very hard to build in principle, but then if you give that to me, I can do awesome optimization if you give me that. I think there's interesting kind of modeling philosophical questions there that also connect very much to different models people are considering in the reinforcement learning space now. A lot of this connects to interesting questions in CS and reinforcement learning, and also just classical control problems considered in applied probability. Again, please come to Stochastic Networks. It's going to be awesome. Thank you all very much. I look forward to the Q&A.
Well, thank you so much, David, for a great talk. Let's start up, as you said, kickstart the questions and answers. We don't have too much time, so feel free to leave us. I will leave the recording a little bit longer so that we can take some time for whoever has the availability.
And I'm happy to stay after. As people know, it would only be fair given consistently dragged out other people's SNAPP seminars by hours at times. So
okay, so I'll go first. So this is in continuation to my previous question about learning the policy, the stopping policy. So
Sure.
You mentioned that the stopping policy is to ensure that the right higher order regret is below epsilon. But how can you calculate this regret? Because you're assuming you have an access to a generative model. So, I mean, when you're learning a policy, I like to think of it as being in two phases. In the first phase, you have access to this generative model, and then that is the training phase. And then once you learn your policy, then you don't have access to this generative model, right? Then how can you calculate this higher order regret?
It is good. So the point is that our expansion gives an automated set of basis functions. It's the same reason why. So let's say I mean, the point is that, let me think about what you're saying. Good. So to implement the policy, you need access to the generative model while you are running the policy. So here you would not be, because, so for example, let's say you just wanted to stop. So a very naive kind of way you could do this would be just stop when your value is close to your best guess of the all-time min at time t. Which would mean that whatever time you're at, you need to be able to compute by simulation E of min given ft.
I see.
Now, admittedly, this is getting at another interesting distinction. I don't know if that distinction has a name. It might. At some point, it became very hard for me to keep track of, like, you know, there's typically 15 qualifiers about which model of reinforcement learning.
What
about,
is
you
it?
know,
Only
it's either
15?
on or off, and it's this and that. So, but admittedly, I actually think that there are very interesting and sometimes subtle connections to exactly questions like that. So that's an excellent question, Siva. And indeed, to implement the stopping policy here, you do need to be able to use the simulator while you're actually going through the problem. If not, it would not. I'd have to.
Okay, I have at least, I mean, I did not come across this kind of assumption, because in reinforcement learning, the literature I'm familiar with, when you assume there is a generative model, you assume access to it during the training phase, but during the testing phase, you don't assume access to it.
Good. So the point here is, like, I mean, it would be the same way that you're building basis functions. But to evaluate the basis functions, you can only do them by simulation. So I guess this is like, you can only evaluate your basis functions using simulation.
I see. I see. So to make it very clear, so what you're saying is that I've done my training, whatever, that's over. Now I want to solve the optimal stopping process.
So I guess, so let me pause, let me even interrupt there. Here it has a closed form. There is no training. E of min, I'm telling you, E of min given ft is the right function to use.
I see.
So, but I agree. This is exactly the last big Q.
Yeah, the last big Q.
How many late night interesting conversations about exactly these philosophical things. Let me give you another one. It goes down a real rabbit hole. And that's like, if you have a Markov chain, what does it mean to ask whether you get to see the uniform which drives the transitions? These kinds of very subtle yet interesting things come up. And again, they're at the heart of a lot of it is, what does it mean to be given a simulator? And what does it mean to have access to a simulator, and et cetera, et cetera, et cetera. And I will say, this also connects to all kinds of models which are not well connected in literature on the adaptive complexity of many kinds of algorithmic things, including in submodular function optimization, the parallel complexity of all kinds of things. Because again, here's another high level thing, which is like, I just know there's something really cool there, is that in some ways, access to a simulator is clearly at a very high level, like having access to massively parallel computation.
Correct.
So there's all this work in parallel computation, and there's all this work in reinforcement learning, and there's this work on adaptive complexity and all these different models. I have the sense that there's some very deep kinds of connections there. And that's exactly that. Good. Very good. Very good. Does that make sense?
Yeah, it does. It does. Yeah. Okay. Thanks.
Hey, Dave.
Hey.
Yeah. No, perhaps I want to follow up a bit on, Siva's question, just to clarify, right? So when we talk about policy, I think what we mean is actually different from, those that you read from these reinforcement learning literature, where when they're talking about policy, it usually means that you have a huge state space, and for each state in that state space, I would like you to output, the action you're going to take in that state, right? But for us, since we're actually allowing our state space to be of a infinite size, so what we really mean when we say that we can compute a policy is that I give you a trajectory of this underlying stochastic process, and you use all these expansion-based technique to compute a time that you're going to stop on that trajectory. That's what we mean by computer policy. Yeah.
Correct. But basically the way it works is you have this real process that's going on. At time 1, you see y1, at time 2, you see y2, at times 3, you see y3, and you have to decide when to stop. But in order to do that, you have the simulator, and then you are running many independent fake copies of this process on your simulator, and then doing your recursive calculations to decide whether to stop at the right now or to go for one more time step. Essentially,
exactly.
And let me even, so Yilun, thank you. Yilun, this is the awesome co-author. He's now a graduated student. So yeah, that reminds me of another rant that I'll give, which is that indeed, there's no thought here to output like as a table for every state what you should do.
Right, yeah.
And I will say though, and that is part of and this is again part of a massive discrepancy in the literature. Because of course, the literature is filled with lower bounds of S times A and things of this nature, right? But very often at the heart of those lower bounds is just the high level sentiment. Well, of course you can't do better than S because you need to output for every state like you do. But, and it's like, it seems there is far less literature on what if you just need to make the decisions on the fly, which is of course all you really ever need to do in principle, in which case you can of course circumvent that kind of, well, obviously you can't do better goes out the window because, okay, maybe you can, right? Very good. Thank you, Yilun. Thank you.
So I had a question which at first I thought was a trivial clarifying question, and I now